Hello, everybody. So yesterday we discussed and hopefully understood how with the unit circle and using equations for circles that we learned in December, we can express this circle as an equation. X squared plus y squared equals 1. And since we know that on the unit circle, all the x values are just cosine values for a certain angle, and the y values are sine values for a certain angle, then replacing x and y with cosine and sine gives us this. So this is called a trig identity. There is a second way to convince yourselves that cosine squared plus sine squared equals 1, and that is by using right triangles. If you create a right triangle inside that unit circle, what have you got? You've got a hypotenuse here, which is 1, right? That's the radius. How long is this leg? Well, it's x over, right? Here's the center. If I want to get to this point right here, I'd have to go to the right an x amount. Well, x is cosine. And then to get up to this point, I had to go up a certain amount. So that's the y value, but y is sine. So I've got a triangle with cosine along the horizontal leg, sine along the vertical leg, and then the hypotenuse is 1. What can I do here? This is a right triangle, so that means that the leg squared plus the leg squared equals the hypotenuse squared. So cosine squared plus sine squared equals 1 squared. And that is a second way that hopefully is very convincing to you that indeed cosine squared theta plus sine squared theta equals 1. We're going to be using that a lot. It's an important trig identity. So, but we just proved it. We proved it twice. So we're never going to prove that this is true. We just get to use it from this day forward. Anytime we have cosine squared plus sine squared, we can replace it with 1. And there are some consequences. If I divided by cosine squared, so if I divide the whole left side by cosine squared and the whole right side by cosine squared, what do I get? Well, cosine squared divided by cosine squared is 1, right? Sine squared divided by cosine squared is tangent squared. Because sine divided by cosine is tangent, and if they're both squared, it's tangent squared. Equal sign, 1 divided by cosine squared is secant squared. So we have what looks like another one, but it's really just the original in disguise. 1 plus tangent squared equals secant squared. And if I go back to this original, and if I divide everything by sine squared, I get cosine squared divided by sine squared, which is tangent squared, sine squared divided by sine squared, which is 1, and 1 divided by sine squared, and that is cosecant squared. So these are called the Pythagorean identities. They're really, all three of them are really the same. They look different, I agree, but they're saying the exact same thing. We keep them kind of separated to help us make it easier for us. But they really are the same thing. Now, when we're trying to prove these identities, we have to be sensitive to squares. Anytime I see a cosine squared, it might be part of this. Anytime I see a tangent squared or secant squared, I might be using this. And similar thing for here. These are the reciprocal identities. We knew these from almost day 1. Reciprocal identities. So these come into play sometimes too. Let's do some practice. How can I prove that this is a true statement? The strategy we're going to use here, we're going to talk about, there's lots of strategies here. For this particular one, we're going to use the Pythagorean identities, and we're going to use this strategy, change everything to cosines and sines. When I was your age, I changed everything to cosines and sines. That helped me through a lot. So that's going to help a lot. That's going to help with a lot of these proofs. Changing everything to cosine and sine. We have to stay on one side of the equal sign. We cannot cross over, because the very thing we're trying to show is that they're equal. So we can't assume they're equal by subtracting cotangent on both sides or something like that. All right, so let's change everything to sine and cosine. I know tangent is the same thing as sine over cosine, and I know cotangent is the same thing as cosine over sine. I think that's true, right? Now, what have I got? I talked about this yesterday. Here I've got a situation where I have two fractions, and my end result, I wanted to make it look like this, which is only one fraction. So, you know, I could write this as a fraction. I can write it as over 1. So I've got two fractions that I want to become one fraction. Well, you just have to add those fractions. So we first have to get a common denominator. So I'm going to multiply this by cosine x over cosine x, which is just 1. I'm going to multiply this by sine x over sine x, which is just 1. And this becomes sine squared x. Oh, sine squared. So if you're thinking about this, good, you should be. Over sine x cosine x plus cosine squared x. Aha, if your brain is thinking about this, good, it should be. Over sine x cosine x. The whole point of being a common denominator was that I can add them up. So now I add them. All right, that's this. So from the beginning, I changed everything to sine and cosine. Once I did that, I recognized that I had two fractions that I wanted to be 1. So I combined those two fractions. I got a common denominator and I succeeded. Now I've got one fraction. So now what? Well, I hope you recognize that sine squared plus cosine squared is just 1. That's the Pythagorean identity. So that's the same thing as 1 over sine x times cosine x. And that's the same thing as 1 over sine of x times 1 over cosine of x. And that's the same thing as the cosecant of x times the secant of x. And multiplication is commutative, so that's the same thing as the secant of x times the cosecant of x. And we did it. That's the proof. If you want a good grade, you have to show the steps. How many steps do I have? 1, 2, 3, 4, 5, 6. 6 steps before I hit the landing of secant times cosecant. No one's going to be impressed that you can skip steps. I mean, I will be a little bit impressed, but this is all about the argument. Remember, you're a lawyer. And just because you really believe or you know that your client is not guilty, that's not good enough. You have to create an argument that is convincing. So don't skip the details. You have to really compose an argument that flows, that gets to the landing that you want to get to. You want to eventually arrive on the other side of the equal sign. Let's try another one. Here, I'm going to change everything to cosines and sines, and that looks like it's going to be all it. Now, you won't be given that. This is just here in the beginning to help us, but I'm trying to convince you that changing everything to cosines and sines is really going to help. How do I make that left side look like the right side? Well, let's see here. If you have an inclination to distribute that sign, that's good. We're probably going to do that at some point, probably. But let's just change everything to sines and cosines first. So sine of x remains. Cotangent is cosine over sine plus cosine of x, okay, over 1, I guess. And then tangent is sine over cosine. So I hope you are following along with cosine of x is the same thing as cosine over 1. tangent is the same thing as sine over cosine, and they're connected by multiplication. Now, the advantage of changing everything to cosine and sine is that sometimes things cancel out, like this right here. Cosine and cosine just cancel out. And then now I can distribute. So when I distribute sine to this term and this term, there are only two terms. Terms are separated by plus signs and minus signs. Well, the first one, the signs cancel out. And I'm just left with cosine of x. On the second one, the cosines are already gone, so it's just sine times sine. And so the right answer just falls right in my lap. That's it. All right, this will be our last one, I think. What are we thinking? You see a secant squared, you see tangent. You've got to be thinking of this right here. 1 plus tangent squared equals secant squared. I would be shocked if using that isn't going to be helpful, because we've got tangents and secants all over the place over here. So let me just, it's so tempting to use that. I'm just going to write it down just so I don't forget. 1 plus tangent squared equals secant squared. All right, now what do I do? I don't know, but I see I can do something. I've got 1 minus tangent squared. So let's just do that. 1 minus tangent of theta times 1 minus tangent of theta. Guys, don't be lazy. You don't write this. I'm taking off points. You're missing the domain. 1 minus tangent of theta. Unfortunately, this is not a difference of squares. It's not 1 plus 1 minus, so I have to double distribute the old-fashioned way. I got 1 minus tangent of theta minus tangent of theta plus tangent squared of theta. These two guys are like terms, so I could do 1 minus 2 tangent of theta plus tangent squared of theta. And I'm keeping one eyeball on this right here to see if I can use it. And I see I've got a 1 plus tangent of theta, so I'm going to regroup these. And 1 plus tangent of theta is the same thing as secant squared of theta. And that is exactly what I wanted to show. That 1 minus tangent squared of theta, 1 minus tangent of theta squared is the same thing as secant squared minus 2 tangent theta.